Hello, and welcome to this VSD presentation on the SkyWater Open PDK. I'm Tim Edwards, Senior Vice President of Analog and Platform at eFabless, and I've been in the business of open source EDA tools and chip design for over 25 years. It is a pleasure for me to be working with the Google SkyWater Open PDK project, as I've been doing since its inception. For decades, I've been developing various open source EDA tools with a limited audience because there was a very limited amount of Foundry-specific information available. Without an example process to use, it's very hard to show how to use the open source tools to design a chip, to design circuits, to simulate pretty much everything, really. In the past, for a long while, starting in the 1980s, the Moses Foundation in California made available the open source Scalable CMOS, or SCMOS rules, which worked with a number of legacy foundries with processes in the range of 2 microns down to about 0.18 microns. But since they've largely stopped supporting scalable CMOS in the past few years, there remains essentially nothing except for a handful of so-called academic processes like free PDK-45. It is very unsatisfying to work on development of a process design kit for a process that can't be manufactured, which is why I've never done it. The SkyWater 130 nanometer Open PDK changes all that. The process has been completely open sourced with all design rules, layer definitions, device definitions and models, device layouts, and other critical process information made available to the public. For the first time, it's possible to work up libraries and setups for open source tools built around a real manufacturable process. Since everyone can see the PDK, anyone who has or uses an open source tool can make it compatible with the Sky 130 process or contribute to that development. This has already happened with the SkyWater PDK, as I will describe in a moment. As I said, I work for eFabless, and eFabless has been instrumental in getting the message about the SkyWater Open PDK out to the public. We have created a design in the Sky 130 process called the Caravelle chip, also known as the harness, which is a system that has a pad frame and a small RISC microcontroller and a large empty space in the middle to take projects submitted by users. Designers can create anything that fits in that space without worrying about details like how to make the pad frame or how to communicate with the outside world. Combine that design with the harness chip using our open source tooling, submit it to eFabless, and sometime later get back an assembled circuit board ready for testing. At least for now and for the near term, this is all paid for by Google, and designers get their boards, custom chip and all, for free, which is a deal that can't be beat. In return for this favor, the only demand from our side and Google's is that the user's design must be made available in a public repository. So clearly, with such a great deal, you want to be part of it, right? You want to make your own custom chip design? But first, you'll need to learn about the SkyWater process and the PDK and learn how to use the open source tools that the PDK supports. So that's why I'm doing this lecture and lab series, to introduce you to the SkyWater process and help show you how to create and verify designs with open source tools so that you, no matter how much of a shoestring budget you work on or how much you squeeze this into your weekends as a hobby, you can make and manufacture your own chip design. First, I would like to describe the SkyWater Sky 130 silicon fabrication process in Open PDK. In case you're not used to working in chip design, PDK stands for Process Design Kit and is a bundle of files and documentation that is needed by a chip designer to know how to work with a particular process foundry and use it to make chips. The 130 in the name Sky 130 refers to the feature size of the process and generally refers to the length of the smallest transistor that can be made in the process, although dimensions of most everything in the process will scale along with the transistors. The name SkyWater refers to the manufacturer, which is the SkyWater Foundry in Minnesota in the United States, up there in the frozen north where I tend not to like to go in the middle of winter. The Sky 130 PDK is divided up over a number of public repositories, but it mainly comes down to 2 major parts: documentation and the PDK libraries and files. There are 3 parts, actually, if you count the community, which you should, because no small amount of collective knowledge about the process is held by the community of users, and the community is made up of open source enthusiasts who are always around and willing to give you tips and pointers and provide help when you need it. Documentation can be found on the website readthedocs.build, and the PDK libraries and files can be found on GitHub. The members of the growing community are currently talking to each other mostly through a Slack workspace. Anyone can join these discussions, and the place to go to join is the URL join.skywater.tools. Google has insisted that the files and formats in the repository are all open source and done their level best to ensure that the files are compatible with open source tools. That means that in most cases, open source EDA tools are preferred over commercial tools. In many cases, the PDK will not work with commercial tools due to the legal complications of posting files in the formats used by the commercial tools. Anyone who has the commercial tools can go to SkyWater themselves, as is the traditional way to get chips manufactured, but that's not the open source way, and that's not what we're all about with the Google SkyWater project. Files and formats only get you so far, so let's look at the tools that are currently working with the SkyWater PDK. First, there's my own wrapper around the PDK files called OpenPDKs, which can be found on my own website at opencircuitdesign.com and on GitHub under my GitHub name, R. Timothy Edwards. OpenPDKs is designed as a makefile-based installer that takes files from the SkyWater PDK and reformats them for any number of open source tools. In theory, OpenPDKs works with any process, open or closed, and any EDA tools, open source or commercial. But per the usual problem with open source EDA tools, there are no other open process descriptions, so OpenPDKs is right now mainly an installer for the SkyWater Sky130 process. There are a limited number of open source tools that work with the SkyWater process, so OpenPDKs does its best to support all of them. Here's how OpenPDKs works. I have gone a long way toward simplifying the whole thing recently so that if you want to get everything installed and set up from scratch, all you need to do are the simple steps of 1. Clone the repo, 2. Run configure, 3. Run make, and 4. Run make install. Since OpenPDKs is still ostensibly supposed to support arbitrarily many processes, specifying the process to install in the second step is needed, but everything else should be worry-free. For the second step, use configure-sky130-pdk to tell OpenPDKs that you want it to compile and install the SkyWater Sky130 PDK from the Google SkyWater sources. The make process will automatically grab the Google SkyWater repository and submodules from GitHub and automatically grab a few other third-party repositories and keep them nearby for using in the install. Then it goes about building libraries from the various individual files in the PDK repository. This can take a long time, but it needs to be done only once. These open source tools are supported by OpenPDKs. Magic is the backbone of the OpenPDKs installer and is the one tool that is mandatory to have installed before running the OpenPDKs makefile. Magic reads and writes a number of different common formats. It does extraction and DRC, handles GDS, LEF, and DEF formats, and can create device layouts from parameterized descriptions, either entered within the layout tool or imported from a schematic. Magic is responsible for creating any file formats of any cells that are missing from the repository sources. Klayout is an alternative layout editor and viewer and can also do DRC. OpenPDKs will install a SkyWater Sky130 compatible setup file and script to do a number of DRC checks. OpenLane is the synthesis and place and route package based on the OpenRoad tools. It's basically a wrapper around the OpenRoad tools with various setups and scripts that support the SkyWater process. Xscheme is a schematic editing tool. It is not directly implemented in OpenPDKs, but is a third-party repository that OpenPDKs can pull in and copy to its common installation location. NetGen is the LVS tool that typically works with a netlist extracted from a layout using Magic and a netlist generated from XScheme or from OpenLane. ngSpice is the analog simulation tool based on Berkeley Spice, and OpenPDKs installs all the model files such that ngSpice can find them with the right include statements.
Anyways, I'll just ask you, I'll be like,
there are a few other alternative tools, including QFlow, an alternative digital synthesis flow, IRSim, a switch-level simulator and power analyzer, and Xcircuit, an alternative schematic entry and schematic capture tool. Additional tools can be added to OpenPDKs either as built-in entries like Magic and OpenLane or third-party entries like XScheme. In addition to the tool setups for open source EDA tools, OpenPDKs will install the Foundry and third-party libraries, creating a directory structure common across all libraries regardless of the source. That's the main goal of OpenPDKs, to have a common file system structure and methods so that all EDA tools can automatically know where to find all the libraries, files, and information that they need. This is especially important for open source tools because they are spread around, maintained by different groups, and not fully integrated. There are upsides to this, but the downside is that methods can get very fractured and incompatible if there isn't a common framework that everyone agrees to work with. The libraries supported by OpenPDKs are SkyWater PDK. This is the basic digital standard cell library used for digital synthesis. There are a total of 7 different digital libraries, mainly designed with different speeds or power operation, although the SkyWater PDK HVL library is for use at 3.3 volts, while the rest are for the nominal core supply voltage of 1.8 volts. SkyWater PDK. This is the library of analog components. Most analog components, such as basic transistors, are handled by extraction and don't need library components. However, many components have one approved layout and are easiest to deal with by treating the device as a component of an IP library. Such devices include RF layouts of basic devices, bipolar devices, ESD devices, parallel plate capacitors, and so forth. Devices operate from 1.8 volts up to 20 volts, with the most common supply voltages being 1.8 and 3.3 volts. SkyWater PDK. This is the library of pads and pad frame cells. It contains power and ground pads, a general purpose I/O pad, and a number of others. The pads operate at a core supply voltage of 1.8 volts and an external supply voltage of anywhere from 1.8 to 5.5 volts. SkyWater MLXX. This is an example of a third-party library. It contains a set of layouts for alphanumerics for use in putting text on a layout that can be seen by inspection under a microscope. Everything handled by OpenPDKs is placed in a common repository with a common file structure. This file structure is by default rooted at /user/share/PDK. So the SkyWater PDK is put at user share PDK SkyWater. The A refers to a process variant, such as a process with 3 metal layers or 4 or 5 or special resistors or whatever. The SkyWater process is designed to incorporate all process options, so there's no point in having more than one setup for the process. So there's only one variant, and it's called A. Under the main PDK directory are 2 subdirectories, libs.tech and libs.ref. Libs.tech contains all subdirectories for the open source EDA tool setups, and libs.ref contains reference libraries. So libs.tech has subdirectories with tool names like Magic, OpenLane, XScheme, etc. And libs.ref has subdirectories with names like SkyWater PDK and SkyWater PDK. Each library has its own set of subdirectories, which are named after file formats. So SPICE for SPICE netlists, MAG for magic.mag files, lib for liberty.lib timing files, lef for lef format files, GDS for GDS format files, and so forth. The subdirectories of the tools is very much tool dependent, so it varies according to the needs of the tool. The device and models follow this format by being split between a library and a tool. The library is SkyWater PDK and contains device layouts in GDS and abstract views in LEF and SPICE subcircuits in a subdirectory called SPICE. The tool setup is under the subdirectory ngSpice and contains all the device models in a format which is ngSpice compatible. The intent of Open PDKs is that there should be a common format for the PDK, but also a common format for projects. The project directory is intended to look much like the PDK directory, so when you start a project, you should create a directory for it, and the directory name should be the name of the project. Under this directory, you can have subdirectories for each of the tools that you need in whatever flow or flows you will use for the project. And these directory names will often be a mixture of tools or file formats. So you may have directories like Xscheme for schematics, Mag for Magic, Spice for netlists. Generally, each tool can be set up for the SkyWater PDK by copying or making a symbolic link from a setup file in the installed PDK. For example, to run Magic, you can copy the sky130a.magicrc file from libs.txt/magic to your project's mag directory and rename it to just .magicrc. Then, if you cd to the mag directory and type magic, Magic will run and load the SkyWater technology and the PDK scripts for generating SkyWater-compatible devices. To run Xscheme, you can copy the xschemrc file from libs.txt/xscheme to your project's Xscheme directory. cd to the Xscheme directory and type Xscheme, and Xscheme will run with the SkyWater analog and digital symbols readily available for drawing schematics. Projects made in several parts can be handled in various ways, and there is, as of yet, no standard for it. Should a subblock be a project? Should a subblock of a project be its own project? Should it be inside a project? Should its design directories be a subset of the subblock or subdirectories of the top-level cell's design directories? Like organizing books in a library, there are multiple ways to arrange things that are equally good and bad. Some project management is called for. That's a longer-term goal of Open PDKs that hasn't been worked on yet. For these lectures and labs, we'll just be working with simple examples that don't have a deep hierarchy, though I'll discuss various issues that arise when a design does have deep hierarchy.
Mint or water? I don't care. I'm not watching either.
Well, we're going to put it now.
Okay, great. But I'm not going to watch it leading up to the meeting.
Yeah, I know, but which one do you want to see? Right now.
The SkyWater Sky130 process is described as a hybrid 130 nanometer, 180 nanometer standard CMOS fabrication process. Mostly FET transistors have a minimum length of 150 nanometers, though specifically designed memory layouts use 130 nanometer long devices. There are 5 layers of aluminum metal plus a layer of titanium nitride, which is used like a metal layer but is relatively high resistance and so not good for long routes. This layer, which is called local interconnect, or LI for short, is probably the most non-intuitive layer in the whole process for anyone used to processes where the first layer of metal above polysilicon is an aluminum routing layer. The general rule for using local interconnect is to use it to connect neighboring devices, but otherwise contact up immediately to metal 1. If you look at the SkyWater standard cell layouts, the local interconnect is used for the power and ground rails, but because it should never be used for routing, the entire length of both rails have local interconnect strapped with metal 1 above them. Contacts to polysilicon are also a little strange in this process, requiring a nitride polycut layer around the contacts. Usually this isn't an issue, but it is possible to place contacts in ways that seem legitimate but cannot satisfy the design rules for the nitride polycut layer. I'll get to describing DRC rules shortly. The metal layers are in a progressive thicknesses, with local interconnect being the thinnest, followed by metals 1 and 2, and then a thicker metal 3 and 4, and finally a thick metal 5. That's a bare minimum of metal layers for this feature size. I'd call it barely adequate. When running digital flows, the tool should reserve metal 5 for routing, and with local interconnect unusable for routing, there are really only metals 1 through 4 to route with. Metal layers in vias are called the back-end layers, and everything below that is called the front end. They are often distinctly separate with different precision required for the masks and, of course, different fabrication steps. They share the steps of oxide growth, which is the insulation layers, but the front end is mainly diffusion and ion implantation, while the back end is mainly metal deposition, usually by sputtering. On the front end, the main difference in use of layers for the SkyWater process versus other processes is that they have divided the diffusion layers into diff and tap layers, where diff represents the heavily doped regions used for example, transistor source and drain, while tap represents the oppositely doped region used for well and substrate contacts. Most silicon fabrication processes do not distinguish between these two, since they're both fabricated with a diffusion method in the same step, and they're only differentiated through different doping levels. There are implant masks for these different doping levels, so the information needed to distinguish a source or drain region from a tap region is already available. Other useful front-end layers to know about are the deep end-well, which is an end-well buried so deeply that there's room to diffuse a P-well region into the area above it. The deep end-well layer then creates a barrier end-doped region sandwiched between the P substrate and the P-well. The isolated region allows P-type devices such as FET transistors, bipolars, and diodes to be completely isolated from the substrate. This isolation comes at the expense of the area required for surrounding the whole deep end-well region with an end-well ring to completely isolate the P-well region on all sides, and a large required spacing between the separate deep end-wells if multiple isolated domains are needed. However, the improvement in noise isolation is worth those drawbacks. The HVI layer is a high voltage implant. It has more than one use. For one, an end-well implanted with HVI is tolerant to higher voltage levels. The mask is also used to grow additional insulation under the gates of MOSFET transistors, forming what is known as a thick oxide gate transistor. The thick oxide devices are tolerant to voltages up to around 5 volts in the SkyWater process, while the nominal thin oxide devices are only tolerant to voltages up to about 2 volts. This leads to typical dual voltage domain designs in which analog circuits are designed with thick oxide devices and run at a common voltage of 3.3 or 5 volts, and core digital circuits are made in the thin oxide devices and run at a voltage of 1.8 volts. The pad frame cells in the SkyWater I/O library reflect this dual domain design methodology with a typical core voltage of 1.8 volts and a pad voltage of 3.3 volts. The MIM cap layers are part of the back-end process, although they form devices that are extracted and simulated from a design standpoint. They feel more like part of the front end. MIM, or MIM, stands for metal insulator metal, and these capacitors are formed by adding metal plates between two metal routing layers. The SkyWater process is notable for having a dual MIM process in which capacitors can be fabricated between metal layers 3 and 4, but also between metal layers 4 and 5, making a stacked capacitor with double the capacity of one layer only. The capacitors are particularly useful because by being fabricated up in the back-end layers, the area underneath them remains available for placing transistors and other front-end components.
But it's like the truth.
There is one other metal layer made available in the SkyWater process. This is called the redistribution layer and is not fabricated by SkyWater, but is fabricated by a third-party manufacturer specializing in the process. Redistribution layers are typically used to form bump bonds, a form of WLCSP packaging, which stands for wafer-level chip-scale packaging. The redistribution metal layer, which is copper, is deposited on top of the finished chip, and solder bumps are added on top of the redistribution metal. The end result is that the die itself becomes its own packaging. No wire bonding is needed. The chip is just flipped upside down and soldered directly to a circuit board with the reflow process. The solder bumps are typically around 1/4 millimeter in diameter. This is a bit smaller than a typical BGA or ball grid array package. And these things are notoriously tricky to solder when the packages are huge, like they are for modern microprocessors and graphics processing chips. But on a fairly small scale, they are not too difficult to work with, and the solder bump size and spacing can be made compatible with low-cost circuit boards. The eFabless Caravelle harness chip was designed with this in mind, with a 6x10 array of solder bumps that is compatible with a cheap 2-layer board. The redistribution layer is usually not a design layer and is considered more as part of the chip packaging. However, the copper layers are thick compared to the underlying process back end, more than 4 microns thick, and can be useful for forming inductors on the top of a chip. In any case, analog designers have to be aware of any redistribution layers on top of a design, and in addition that the chip is flipped with circuit board, power, and ground planes directly underneath. Understanding the devices is important for physical verification, since much of the physical verification is concerned with correctly identifying and extracting all devices on a chip. I already discussed some devices available in the SkyWater process, namely thin oxide and thick oxide MOSFETs and MEM caps. Like most larger feature-sized processes that are good for analog and mixed signal design, the SkyWater process has numerous device offerings for resistors, bipolar devices, capacitors, and so forth. The best bipolar devices, that is, devices with high enough beta to be useful, are vertical bipolars, making use of the NP junctions between diffusion regions and wells. Processes like the SkyWater 130 nanometer process that have deep in-well layers can have properly isolated NPN transistors, with the NPN layers being an in-diffusion layer for the emitter, a P-well for the base, and the deep in-well as the collector. PNP bipolars are limited in use, as the only configuration requires that the collector be grounded, as it is tied directly to the substrate. The best resistors are made with doped polysilicon. There are 2 specialty devices in the SkyWater process. One of these is a P+ doped poly resistor with a sheet resistance of around 1 kilo ohm per square, and there is a P- doped poly resistor with a sheet resistance of around 2 kilo ohms per square. For some applications, diffusion resistors are appropriate, but since they have a PN junction underneath, they must be used in circuits designed specifically to keep the junction firmly reverse biased. The highest resistance per square is the P-well resistor, but due to the large size and spacing requirements for the P-well layer, it is rarely a practical choice, especially when high sheet resistance poly resistors are available in the process. One oddity of the SkyWater process is that most devices have a discrete set of sizes that have valid corresponding models. In other words, devices aren't characterized across a continuous change in width and length. For a number of the devices, using a device size that is not one of the valid characterized sizes is not even allowed. The precision resistors, for one, come in 5 discrete widths that correspond to a layout around an integer number of contacts. Devices with a restricted number of approved layouts are not all that uncommon in process PDKs. Typically, a number of devices are carefully laid out and thoroughly tested, and that layout becomes the single reference design. Those devices are passed on to the user by the foundry as GDS files, and the user is expected to use those layouts as is without touching them. There are a number of mask layers that are specific to a handful of devices with fixed layouts. Because of that, most layers really don't need to be shown to the designer. Most such layers are identifier layers, such as the capacitor or resistor or bipolar identifiers. They need to cover the device but have no design rules associated with them, other than that they need to cover the extent of the device. The designer should not even need to know that an identifier layer is there.
Pero eso es tremendo. Y por ahí te parece seguir una canción. Ah, ¿no sabes qué hacer aquí?
Es una de las cosas
No, vale. Pero usualmente cuando hacen land, lo hacen en el Middle East. No, you don't. Yeah. Land in the ocean. Crash landing. Me acuerdo viendo algo así, ¿verdad?
California, Nevada.
It's distracted. Yeah, home, son.
No, pero ese va así, ya puede caminar. Suena en esos tiempos, seguramente. No entendía cómo funcionaban las cosas.
¿Es este el tour? ¿Es el de la
Yeah.
¿Es el tour de la lala?
No, I'm thinking. Oh, shoot. ¿Solo mi lata? Yeah.
¿Hace cuánto tiempo?
Terrifying. What is right about
The SkyWater Open PDK is distributed along with a number of complete IP libraries from the Foundry. The library should contain everything that the user needs to work with that IP. There are 3 types of libraries immediately available in the SkyWater PDK: digital standard cell libraries, I/O cells, and primitive devices. The digital standard cell libraries all come with layout of every cell in GDS form and files that are normally used by digital synthesis flows, such as Liberty timing files, LEF technology files and abstract cell views, Verilog descriptions of the cells, and SPICE or CDL netlists. There are various flavors of digital cells, 7 of them in all, covering a range of uses from low power to high speed, high density, high voltage, and low leakage. The libraries all follow a standard naming convention, and all cell names and device names contain the library name as a prefix. The library names are in the form of Sky130_vendor_library type, and then optionally another underscore and an abbreviation for the library, if there is more than one library per type. So the most commonly used digital library, the high-density standard cell set, is named Sky130_FD_SC_HD, where the FD stands for Foundry, meaning that the Foundry is the vendor providing the library IP. SC stands for standard cell, which is the library type, and HD stands for high density, which is the specific library name. The library name prefixes all of the standard cells, so the standard cell name may be, for example, Sky130_FD_SC_HD _NOR2_2, where a double underscore is used as the separator between the library name and the cell type. The NOR2 is the cell type, which is a 2-input NOR gate, and the last _2 refers to the amount of current drive in the output of the gate, which is not a unit of anything, but just a relative designation. Lower numbers have weaker drive output, and higher numbers have stronger drive output. Typically, it's the synthesis tools that worry about what drive strength to use, not the user. For the designer using digital standard cells in a schematic, you can figure out from simulation if you have sufficient drive strength, or just use a rule of thumb based on the fan out of the gate. Also, for the design using digital standard cells in a schematic, be aware that the standard cells are designed specifically to be placed in a row, so any manual layout containing standard cells should treat them the same way, placing them next to each other according to the abutment bounding box, and not overlapping or spaced apart. There is, unfortunately, almost no documentation on these standard cells. In most cases, the digital synthesis tools have the information they need, and the designer doesn't much care which cell is which. But it's always good to have some reference to understand, for example, the naming conventions of the AND or invert gates versus the OR and invert gates, and so forth. Plus, there are a number of specialized cells for working with standby power and voltage isolation of inputs and such without any good reference as for how they're supposed to be used. Also, there are no symbols in the SkyWater libraries for making schematics, but we do have some third-party sources with symbol libraries, and the Open PDK's installer will use those to supplement the vendor libraries. That helps somewhat to overcome the lack of documentation. Another important library is the I/O cell library. The SkyWater 130 nanometer process has a particularly complicated set of I/O cells that are a legacy of a series of chips designed by Cypress Semiconductor. They have a number of unusual features, and many of those features are not going to be of interest to most designers. The eFabless harness chip design exists as a good reference on how to put together a pad frame with these cells. I would recommend for most people to use a reference design like the Caravelle harness chip to figure out how to wire up the I/O cells. There is extensive documentation on the I/O library, but I found that it takes a good 5 or 6 readings to start getting a thorough understanding of the cells and how they work. The name of the I/O library is SKY130_FD_IO, which, now that I've explained the naming convention, should be pretty obvious. One problem with the I/O library from SkyWater is that it contains power and ground pads, which have entire disconnected blocks in them. You'd expect, for example, that the VDD-IO pad cell would be connected to the VDD-IO ring going around the pad frame. But no, there's an overlay cell that is needed to connect the VDD-IO pad to the VDD-IO bus. There is also an ESD voltage clamp in the same cell, but it's not connected to any power domain. So if you want the VDD-IO pad to connect to the VDD-IO ring and also have a VDD-IO power clamp for ESD protection, there's supposed to be another overlay cell for that. Only those overlays don't exist. Fortunately, the OpenPDK's installer takes care of those problems by supplementing the I/O library with a set of cells that include the missing overlays and other cells which conveniently combine the base cells and the overlays together so that you don't need to worry about the details of that connectivity. For most purposes, you'll just want one of those combined cells, which have the most common configuration, such as the one that I just mentioned, where the VDD-IO pad cell connects to the VDD-IO ring and has a VDD-IO power clamp. Those supplementary cells were made by eFabless for the Caravelle harness chip, so by the naming convention, these cells are prefixed with SKY130_EF_IO, where EF stands for eFabless, which is the vendor providing the cells. But since those cells are designed specifically to be used with the SkyWater I/O library, the OpenPDK's installer puts them in with the rest of the SkyWater FD-IO library. The primitive device library, which is named Sky130_FD_PR, where PR stands for primitives, contains devices which, as I mentioned earlier, have very specific layouts that are approved by the vendor, which in this case is the foundry. Those layouts include regular transistors with layouts that are optimized by best practice design for RF or radio frequency use. That generally means carefully controlling the parasitics to avoid signal attenuation or noise coupling through parasitic channels. Other specific device layouts in the primitive library can include bipolar transistors, varactors, high voltage drain extended devices, ESD devices, and an astonishingly large and confusing array of parallel plate capacitors of all shapes, sizes, and metal layers. I would tend to advise against using the parallel plate capacitor simply because there are MIM caps available which have a much higher capacitance per unit area without taking up all the routing area above a design. There are 2 libraries that have not been distributed with the SkyWater PDK yet. These are the SRAM and NVRAM libraries. The SRAM library has been handed over to the OpenRAM project. The original sources from the foundry included only the core SRAM cell layout, and so the OpenRAM project is creating the additional cells needed for the decoding and driver circuitry. Eventually, these cells will be put together in a library and either added to the SkyWater PDK or maybe just left as a third-party library. We have even less of an offering from SkyWater for the NVRAM, which is to say non-volatile RAM, such as Flash EEPROM. What we have is really not much more than just the design rules for the floating gate Sonos transistor. An NVRAM library would need not only the same basic decoding and driving circuits as an SRAM library, but it needs additional circuitry for the high voltage charge pumps and circuits to control the programming and erasing.
Yeah, because you say
So
it
that
so
library
much
is
that it
likely
seems
to be a much
unnatural.
longer time in coming.
Are you here for Gemini? Yeah. Yeah, me too. Oh.
So that's what's being offered in the SkyWater PDK. As I said, the file formats that are posted are specifically chosen for the ability to be open sourced, which is to say non-proprietary formats, and so they should be able to be used with open source tools. EDA tools, whether commercial or open source, are not really known for their variety of offerings, but there are a handful to choose from, so I'll do my best through this course to introduce you to them and show you how to use them. So, say you want to create a chip. Okay, no, wait, let's start a bit simpler. Say you want to design a circuit. Let's keep it basic, no microprocessors right now, just some simple analog circuit to do some basic task. There's a real foundry process here, and actually you can use the eFabless Caravelle harness chip and put your circuit on it and submit it to eFabless and get it manufactured at SkyWater. But that's getting ahead of ourselves. First, you want to design the circuit and make sure it works. You'll need to know what tools you can use to do the design and do a functional verification, which means that it will behave like you want it to in terms of signals, voltages, inputs, outputs, and such. And finally, to do a physical verification, which means to check to make sure that you have a mask layout that matches what you think the circuit is supposed to be. The remainder of this lecture series will be primarily about physical verification, knowing what software is available that does it and how to drive that software. I'll start off by describing a simple manual design flow, and then there will be a corresponding lab exercise that you can do to show that you understand the steps of this flow. The circuit to be designed in the lab is nothing extraordinarily complicated. The purpose of the lecture and lab is not to show you how to do analog design, but to show you how to run the tools and how to do physical verification. Since to do physical verification, you have to have a layout to verify, the first thing we'll do is to create a layout. Before the lab, I'll give a brief overview of the flow, and then the lab will be spent with a much more detailed description of how to run the tools to create the layout. For even basic analog design, there is not yet very much automation to the process. We'll assume a circuit that has a handful of transistors, resistors, and capacitors, maybe even a simple mixed signal circuit with a few individual digital cells and maybe a small bit of hierarchy to it. The circuit will have a schematic, and the schematic will represent all the devices and a hierarchy that usually, but not necessarily, tracks the hierarchy of the layout.
That would scare me.
In the lab, we will use a tool called Xscheme to create the schematic, where Xscheme is the tool that I mentioned earlier, which has a set of corresponding symbol libraries for the SkyWater process, provided by the Xscheme tool developer, Stefan Skippers. Isn't open source great? Xscheme is well integrated with both ngSpice, the simulator, and GAW, the waveform viewer, so barring a deep analysis of the device physics, you have everything that you need to design and functionally verify a working analog circuit. The first automation occurs at the device level. You have a schematic and you want a layout. The schematic is something that can be used to generate a netlist, and the netlist can be simulated, say, with ngSpice. The same netlist in SPICE format has all the information needed to know what the devices should look like in a layout. For the layout, we'll use the tool Magic, which is a largish piece of software written in the 1980s, which I've been developing since the 1990s. We'll use this because the SkyWater 130 nanometer PDK in the OpenPDK's installer comes with a set of interpreter scripts written in the TickleTK language that tells Magic how to draw a number of device layouts. The PDK is written so that the device drawing procedures can be kept in a file and sourced at the time the program starts. Each device requires a set of routines to describe it. Each device is heavily parameterized so that the way the device is drawn depends on the way the parameters are given to it. Some of these parameters are the same parameters that you have control of in the schematic drawing program, length and width of transistors, for example, and number of fingers. Other parameters are very layout specific and don't appear in the schematic, such as where to put contacts or whether to add a guard ring and whether to contact pins up to a routing layer. It should be clear from that description that automation can get you partway from a schematic to a layout by providing some of the parameters from the schematic design, but other parameters will have to be provided manually based on what the layout looks like. Such automation is possible, of course, but also very, very complicated. So the starting point in creating a layout is pretty straightforward. You have a schematic, you export it to a netlist. Then you import that netlist into the layout. Without a sophisticated analog placement tool, you get, at best, a grouping of devices that you will have to sort out yourself. The next step in the manual flow will be to move the devices around in the layout until they pass DRC checks, something I will cover in much more detail in the next 2 lectures, and then to wire them together. That's essentially the whole layout process, although there are plenty of details to consider that concern matching of devices or preventing injection of noise and so forth. Those are advanced topics of design, and I'll gloss over most of them to get to the part about physical verification. The final step will be to run LVS. Again, this will be covered in much more detail later in the next and in the last lecture and labs. LVS takes on a number of forms, but in this case we'll be doing the traditional one, which is comparing a layout to a schematic. Of course, a layout and a schematic are very different forms, so we will have to have a way to get them both into some common format so that we can compare them. That common format is the netlist, specifically the SPICE netlist. Better yet, we have open source tools that know how to deal with files that are ngSpice compatible, so we can verify with the same netlist that we simulate with. From the schematic side, we already had to generate a netlist for simulation that used that same netlist to create the devices that were imported into the layout tool to seed the layout. From the layout side, we use a method called extraction, which, in this case at least, is built into the layout tool. We'll issue a set of commands to the layout tool, and from that we'll get a second netlist that describes the circuit as the layout tool sees it. How the layout tool knows what a device is will be a topic for the next lecture. It's not sufficient for the schematic to just pass along the information. The layout tool has to look at the actual mask layers in the layout and decide for itself how those layers interact to form devices, with no prompting and ideally no additional information above and beyond the actual mask layers in the layout, so no cheating. Now you've got two netlists that were derived from independent sources. One is a schematic that is drawn with symbols, and the other is a layout drawn with mask layer geometry. Now we run the LVS tool, which compares these two netlists and tells us whether or not they are equal to each other. If they are, then we're done. If not, then we have to analyze the result of the LVS tool and determine what went wrong, fix it, and repeat until the LVS tool says that the two netlists match. So apart from completely glossing over any details having to do with the electrical design, that's the complete flow from schematic to verified layout. Not running DRC checks won't get you very far because a design that doesn't pass DRC checks will get rejected by the foundry and you'll never get your chip into fab. Not running LVS checks won't be noticed by the foundry, but it's dangerous to just assume that your circuit is correct without having tools to confirm it. Running LVS is critical for having some confidence that the circuit you designed will work right once it's manufactured. We'll now proceed to the lab and work through a simple example. That will let you get used to some of the important tools that will be used for physical verification, and get used to what layouts look like in the SkyWater process, and what devices are available, and what they look like both in schematic or symbol form and in physical form on the layout. Welcome to the lab portion of the first lecture on the SkyWater Open PDK and physical verification. As outlined in the lecture, the lab will focus on several things, mostly to get you used to the SkyWater PDK and the open source EDA tools that will be needed to do physical verification. This lab will follow a simple analog circuit flow. The purpose of the lab is not to make the most compact or the most beautiful circuit layout or even a correct circuit. Although you should take a good stab at making a correct circuit, the physical verification is what is ultimately going to tell you if something is wrong and guide you to a correct result, and that's what you're supposed to learn. Since you're working on a cloud-based platform, you're not expected to do an installation of the PDK yourself, but the files and tools on the system are the same as the ones I outlined in the lecture, made by getting the OpenPDK's installer and following the instructions to build the SkyWater PDK. The make process in OpenPDKs will do the work of obtaining the SkyWater PDK sources and other third-party repositories. So while you'll use the VSD platform as a virtual sandbox to play around in, this is something you absolutely can do at home. Note that all the tools being used are designed to work on Linux systems and should work readily on standard platforms like Ubuntu, Debian, CentOS, and so on. With some good web searches, you should probably be able to get this all working under Mac OS or Windows 10 using WSL, but if you do that, you'll be largely on your own, as all the install instructions assume a stock Linux system. Since in your VSD sandbox, the PDK and the tools are already installed, I'll mostly be showing you how to run the tools, but I'll also explain where all the PDK files are that the tools are using. If you were doing this yourself, the first step would be to clone the OpenPDK's repository from GitHub and then build it on your system. Also, you would need to know what tools you're using and where to get them. Most tools are available on GitHub. Some, like the ones I develop, are kept elsewhere, but GitHub is a mirror site, so either way you can find them on GitHub. Many of the tools have packaged versions, but in most cases the packaged versions are out of date. The release of the SkyWater PDK means that most of these tools have been undergoing rapid development in the past year to ensure compatibility with the SkyWater PDK. The tools are seeing an uptick in users, so bugs are being uncovered and fixed at an increasing pace. All of that means that you will have the best experience if you get the latest versions of the tools, and that means compiling them from source. If you're interested in embracing the open source movement and building your own chips with open source tools, then you will need to get used to the idea of pulling and updating tools frequently and always compiling from source. It's an essential survival skill in the open source world. Another survival skill in the open source world is to get used to doing most everything from the command line, and then when you find that you do certain tasks repetitively, go write up those commands you do often into a script that can be run. The OpenPDK's installer is full of such scripts. Most of them are a combination of Tcl and Python, which are the two interpreter languages most often used in EDA tools. If the commands for the tools are in Tcl or Python, then you should be able to collect the commands into a file and then source it from the appropriate tool. All of the tools we will use have a command line. Some of them are graphical and have interfaces with menus and events done through mouse clicks and motion, but there is still a command line underneath. Most of these tools are written with the expectation that the command line is better than a GUI because the command line is repeatable, while actions in a GUI are not. For the first exercise, check that these tools exist by bringing up a terminal and typing the name of the tool as a command. They will not necessarily come up in a usable state. The purpose of the pre-exercise is to determine that they exist. Magic, NetGen, XSkim, and ngSpice. We'll start with Magic. Type Magic on the Linux command line. You should get two windows, one of them a layout window and one a console window. The console window has a command prompt and is a stock Tcl interpreter in addition to running commands related to layout and related actions. There. To quit Magic, you can go to the File menu and click on Quit, or you can just type Quit at the command prompt. Next, try NetGen. Type NetGen on the Linux command line. NetGen is all command-driven and has no graphics interface. Like Magic, its command window has a command prompt and is a stock Tcl interpreter, as well as running commands related to LVS. And like Magic, you can quit by typing quit on the command line. Next, try XSkim. XSkim is much like Magic and NetGen, except that the Tcl command prompt shows up in the console instead of a separate window. Also, unlike Magic and NetGen, it does not have an application-specific quit command. So to exit XSkim, you will need to type exit, which is the native Tcl command for exiting the interpreter. You can also exit by using the menu option File Exit. Next, try ngSpice. Type ngSpice on the Linux command line. ngSpice has its own prompt and runs its own small set of interpreter commands. It is not a Tcl interpreter or any other commonly used interpreter. Like NetGen, there isn't a whole lot you can do unless you have a circuit prepared for input. So for now, you can just type quit. You'll presumably have noticed that Magic and NetGen have very similar user interfaces. With nothing else given on the command line, both will bring up a console window with a Tcl interpreter. Both accept the command line quit to exit. XSkim is similar, but the Tcl interpreter prompt is in the terminal rather than a console window. You can get this behavior in both Magic and NetGen with the -no console option. So try Magic-no console and NetGen-no console. Magic can even be run without graphics. Try magic-d-null-no console. This is the way Magic should be called if running from a script. You can give it the name of a script to run on the command line, which also works for the other major applications. Create a very simple command file by doing cat >test.tickle and typing quit followed by Control-D. Or if you prefer, you can create the file in a text editor like Nano or Vim. Now you can use this script to see how each of the main tickle-based applications can be run in batch mode, such as magic-d-null-no console test.tickle, or netgen-batch source test.tickle, or xscheme-tickle test.tickle, scratch that, -q. Note that quit is not a tickle command. It is a special command extension added to the interpreter by Magic and NetGen. Xscheme doesn't add this, which is why the batch command above throws an error when running. ngSpice is an interpreter, but it has its own bizarre and limited interpreter language, which is not tickle and it's not Python, and you'll have to look at the ngSpice documentation to understand it. ngSpice can be run in batch mode too, although without input it won't do much good, but here's the command, ngSpice-b. NetGen has a GUI which is written in Python and can be run as the command /user/local/lib/netgen/python/lvs_manager.py. I will discourage the use of the GUI though, because it hides numerous options that we will want to learn about in detail in an upcoming lab. Also, it violates the principle I cited above by being a pure GUI and not having a command line interpreter prompt. When you run Magic, note that it says it has loaded technology minimum and has a handful of icons on the side. Get that up on the screen. This is not a valid setup for doing layout. The other tools are likewise not able to see the SkyWater PDK, although maybe not so obvious about it. We'll be looking at how to make the tools aware of the PDK next. There will be 5 lab exercises. The first one is a warm-up exercise to show you how to set up a proper project space and configure the tools to work with the SkyWater PDK. The other 4 exercises will be using the tools we have run. Xscheme to make a schematic and simulate it, then export from Xscheme to Magic to create a layout, then run Magic to finish the layout, extracting the netlist in Magic and simulating it, and then run LVS to confirm a match between schematic and layout. This runs through all of the steps of both electrical and physical verification with only a couple of devices. The purpose is to understand how to use the tools and how to run the various steps of the flow. We'll start with a simple circuit with just a few devices and no hierarchy as a warm-up exercise. First, go to your home directory. Then create a project. We'll do just about the simplest thing possible, which is to create an inverter. So let's first make a directory for the project, and we'll call it inverter. For OpenPDK's compliance, the preferred method is to have a directory for each tool, so do the following: cd inverter and make dir xscheme, make dir mag, and make dir netgen. Now we want to set up each directory so that you can run the appropriate tool and it will come up properly configured for the SkyWater project. For xscheme, cd to xscheme, and link --symbolic user share PDK sky130a libs.tech xscheme xschemrc. We'll do ngSpice simulations from xscheme, so we want the proper ngSpice setup as well. So do links --symbolic user share PDK sky130 libs.tech ngSpice spinit space.spicinit. For Magic, cd /mag and link symbolic user share PDK, sky130a, libs.tech, magic, sky130a.magicrc, space.magicrc. Note that in this case, the local name is not the same as the file name in the installed PDK directory. For netgen, cd /netgen, and link -symbolic, user share PDK, sky130a, libs.tech, netgen, sky130a_setup.tcl, space setup.tcl. In all cases, the tools can be run with appropriate command line options and know where to find the SkyWater PDK. But with the links, they can find the PDK automatically, and you don't have to remember the command line arguments all the time. Now test the setups. cd to /xscheme and run xscheme. You should now see a display in xscheme. It has lots of example schematics and introduces you to Sky130 devices. If you see that rather than a blank layout, then you've got it set up correctly. I will be guiding you through a set of simple examples in xscheme, but if you want to explore the PDK setup, there are a number of examples that you can look through. In the set of examples shown on the left side of the window, click on the rectangle and type the key E for enter. To get back to the original page, type Control E. The same can be done with any of the examples. Once you're done, exit xscheme, and then go to the mag directory, cd.mag, and type magic. Now the top bar in the window should say Technology Sky130, which I'll need to expand the window to show. And you'll see a bunch of colored squares on the right, which are the layers of the technology. There's the technology name, and these are the layers. Before you exit, note the colors and the patterns of those icons. Now you can quit. And now do magic -D XR in caps. This looks very much the same, but if you were paying attention, you should see that the icons have much more saturated colors. The -D XR option invokes the Cairo graphics package and uses 3D acceleration to get much better rendering than the default graphics. With a virtual desktop, this may not be hardware accelerated, but that won't matter much for these simple examples. There is another graphics package for OpenGL, which is invoked with the command line magic-D OGL. It is much less likely to work over a VNC server, although if it does, it is usually a bit faster than the Cairo graphics. Going back to running magic with magic-D XR. While you're here, if you're not familiar with the magic cursor box, then use the mouse buttons 1 and 3 to change the position and size of the white box in the middle. Since magic starts out with a very close-up view, you will probably want to type Shift-Z to zoom out several times so that you can see the whole cursor box. Magic commands variously operate according to either the position of the pointer or the location of that cursor box. The cursor box is, in effect, attached to the layout, while the pointer isn't. Move the pointer over to one of the icons on the side and either click the middle mouse button, or if you don't have a middle mouse button, then type the P key while you have the pointer over the icon. You should see the name of the layer of the icon you're in on the top bar, and when you type P or click the middle mouse buttons, you'll see that the white cursor box just got filled in with that layer. That's called painting. Now, with the right and left mouse buttons, move the cursor box partly over the area you just painted. Now you can either move the pointer back to the icon with the same layer you just painted and type E to erase, or move the cursor anywhere over an empty area of the layout in the layout window and click the middle mouse button, which will also erase the layer. We are not going to get much more complicated than that with painting and erasing layers in this lab exercise, so if you did that correctly, you're all set. Make sure you know where the purple colored icon is. If your window comes up with the icons running off the bottom of the window, like mine just did, then go to the menu item Options, Toolbar, and disable the toolbar, then re-enable it the same way, and all the toolkit icons should show up. Put the pointer over the purple square to see the name in the top bar is Metal 1. This is the layer we'll use to connect up devices later. Now that you know how to erase what you just drew. I just did that using the method of clicking the middle mouse button while hovering the pointer over an empty space in the layout. Although we'll create devices automatically from schematic in this lab, it's good to know how to do that by hand when you need to. Another check that the PDK has been installed properly is that there should be two menu buttons labeled Devices 1 and Devices 2. These buttons are how you create devices in the SkyWater PDK. Click on either of these and you get a drop-down menu list of options. Now click on Devices 1 and then MOSFET. You should get a pop-up window with a bunch of checkboxes and boxes where you can enter values. Try changing a few of them, such as width or length. For example, change width to 2, length to 0.5, and fingers to 3. Then click Create. You will probably get something large filling the whole window, so put the pointer back in the layout window and type V for View, and it should zoom out so you can see the devices you just created. If you see a 3-fingered MOSFET surrounded by a guard ring, then you did it right. If you didn't click on Create and Close, the window is still up, so you can still change things in the parameterized device. If you did close the window, you can always reopen it on a selected device by typing Control-P. Say, to get rid of that guard ring, uncheck the box Add Guard Ring, and then click the Apply button. And that should make the guard ring disappear. Want a 5-volt transistor instead? Click on Device Type up at the top, where you will get a drop-down list of similar devices, all InFETs. Click on the item Sky130 FDPR InFET G5 V0 D10 V5 and click Apply. Although the differences are not obvious, the device is now a 5-volt FET with the HVI implant layer to make it 5-volt tolerant. The way to tell what the device type is, other than looking at the device parameter window, is to hover the pointer over the transistor gate and type the key S for Select. Then, in the command window, type What, and you should see that the device is type NV-NMOS, which stands for medium voltage NMOS. Also, it tells you what cell the layer is in. Another quick note about using Magic. You don't have to keep moving between the layout window and the console window to type commands. If you're working in the layout, just type the colon or semicolon key to start a command. So if I'm hovering over another part of the layout, I'll just type semicolon and then type a command without moving to the command window, and the command gets typed in the command window automatically. Everything I type will go to the command window until I hit the Enter key. That's enough about Magic for now, so we'll stop there and come back to it when we have a schematic and are ready to turn it into a layout. So quit at the Magic prompt. We don't need to save this test layout, so you can just click Yes in the pop-up prompt window. As for checking the PDK setup with NetGen will not read the setup on startup, so there's no way right now that we can determine if the setup is correct. We'll get to that later. ngSpice has no special setup at all and knows nothing about the PDK. It will have to be told where to find the PDK devices and by include statements in the netlist files given to it. We'll get to that presently too. Now to use the schematic editor to create a new schematic. first get back to the Xscheme directory. So cd to /xscheme and start Xscheme. I'll resize the window, and I like to hit the F key right away after resizing the window to my taste to make the schematic fill the screen. But we won't be using these examples. So go to File, New Schematic. The way to add components in Xscheme is to use the Insert key on the keyboard. Press that now. The window should be pointing to 3 different locations where Xscheme libraries are stored. One of them is the default Xscheme library and contains non-PDK specific items like input-output pins, power supplies, and other various test bench components. One of them is the current working directory. If we were making a hierarchical or complex design, then there would be additional schematics and symbols here that we could use. For now, it's empty. The last library is the SkyWater PDK. Click on this one to start. The library has a number of subdirectories matching the SkyWater library names, which I covered in the lecture. We're going to place some low-level components, meaning primitive devices like the one we just created a layout for in Magic. So click on Sky130 FDPR. For an inverter, we'll need one InFET device and one PFET device. Which one you choose doesn't matter for the example, but generally you should be using the InFET and not the InFET 3, since the InFET is a 4-terminal device and shows exactly where the bulk terminal is connected. If you use InFET 3, then the bulk terminal is a parameter, and you'll need to make sure it matches the name of the net that is supposed to be attached to. To start with, I'll pick up the standard 1.8 volt InFET. To place it, I just click on OK, and then find a place to put it down, so to speak, and click the left mouse button. Now I go back to the library window with the Insert key and scroll down to the PFETs and choose the 1.8 volt PFET device. For variety, I'll choose the PFET 3 device. As I mentioned earlier, I don't recommend it, and I especially don't recommend mixing the 2 types as it makes the schematic confusing, but I want to show you how to configure each type correctly. I'll put the PFET above the InFET in the schematic, being careful to line them up. Now I want input and output pins. It may be tempting to start putting in voltage sources and so forth here on the same schematic. However, remember that we want to turn the schematic into a layout. The best practice is to keep the circuit part that will be turned into a layout self-contained so that it doesn't have any components in it that wouldn't be part of a layout. The other best practice is not to use any specific power supply pins. It is very convenient to use global names in a schematic, but that doesn't reflect what the layout will be. There is no concept of a global net in a layout, and using them in a schematic can only cause trouble with layout and verifying your circuit later on. The pins are not PDK specific, so you'll need to click on the libs key to get back to the list of libraries. Then click on the Xscheme library entry and click on the devices subdirectory. Scroll through this list to find the entries for iPin, OPin, and IOPin. Grab an iPin and place it on the schematic. If you need to move it, hover over the pin and type the M key to move the component somewhere else, like this. Do the same with an O pin with the Insert key. Select and place it at the end. Do the same with the I/O pin component. Insert key, select, and OK. A quicker way to make another I/O pin is to hover over the I/O pin and type the C key for copy. Then move the new I/O pin and place it with the left mouse button click, like so. If you need to delete something, select the component you want to delete and then use the delete key on the keyboard. To wire up the components, use the W key. Hover the mouse over the point you want to start a wire segment and type W. Then drag the end of the wire to the point where you want the end of the wire to go and click the left mouse button. Do this to connect up all devices and pins. Don't forget to connect the bulk terminal of any 4-terminal devices you used. Now change the pin names to something sensible, not to mention unique, by clicking on each pin and typing Q to get the parameter window. In the parameter window, you just need to replace XXX in the label name with the pin name of your choice. I'll use in and out, VDD, and VSS for my 4 pin names. Now we should configure the properties of the devices. Start by clicking on the InFET device to select it and type Q. The default L equals 0.15 is not allowed for devices outside of SRAM, so let's change that to 0.18. Again, just by replacing the text. For the end device, change W to 1.5. And for kicks, let's set NF to 3 fingers. Be sure to note that the SkyWater PDK uses BSIM model FET devices, and for BSIM devices, W is the width of all fingers combined. So if we want 3 fingers at 1.5 microns each, W needs to be changed to 3 times 1.5 or 4.5 microns. All the other parameters are layout specific, and the schematic symbols in X scheme use default values based on other parameters so that a simulation made from the schematic will have reasonable values, so leave these alone. For the PFET, use 3 fingers of width 1, so set NF to 3, and then W will need to be set to 3 times 1, or 3. Also change L to 0.18. Note that I used the 3-terminal device here, so instead of the 4th terminal being wired up to the power rail, I will specify the power rail as a parameter of the device. Body is already set to VDD. To be pedantic, I'll change that to lowercase to match the pin name, although the netlist will be SPICE, and SPICE is case insensitive, so it doesn't really matter. Now we have a valid schematic for an inverter. Save it using File, Save As from the menu. In the window, change untitled.sch to inverter.sch. By default, the local directory is chosen for the output, which is what we want, so click on OK. This is the schematic that we want to create a layout of. However, we also want to functionally validate the circuit. For best practice, as I mentioned above, you want to have a test bench that is separate from the schematic circuit itself. The schematic circuit will appear as a symbol in the test bench schematic. So the next thing we need to do is to create a symbol. Go to Menu Symbol and click on Make Symbol from Schematic, and then confirm with OK. Now start a test bench schematic with File, New Schematic. Do Insert. Click on Libs to go back to the library list. Click on the current directory entry, then click on inverter.sim. Type OK. Click OK. There are lots of ways you can edit your symbol to make it look nice and put pins in better positions and so forth, but I'm just going to use the default for this example. The test bench is going to be pretty straightforward. Set a power supply, then ramp the input and watch the output response. Get the voltage supplies from the default Xscheme library. So we'll go to vSource, click OK, make 2 voltage sources, and connect one to the input and one to the power rail. Connect up the ground and force the ground node by getting a ground symbol from the library and attaching it to the ground net. Create pins for those signals you want to see in the ngSpice output, which is going to be the in and the out signals. We'll use O pins for these. Now change the pin names to what you want. We'll just keep the names out and in. Now, to make a proper SPICE test bench, it needs to have something telling it how to do the SPICE analysis. The first thing we'll do is to set the voltage sources. The first one is easy. Click on the voltage source for VDD, type Q, and set the value to 1.8, since this uses low voltage transistors, which are only supposed to be powered to 1.8 volts. For the input, set a voltage sweep by setting the value to a piecewise linear function. Since the PWL statement has spaces in it, we'll need to enclose the whole value in quotes. I'll write quote PWL parenthesis 0, 0, 20N, 0, 900N, 1.8, close parens, and close quote. The PWL statement has pairs of time voltage values, so this statement will make a voltage starting at 0 and then at 20 nanoseconds ramp up until it reaches 1.8 volts at 900 nanoseconds. Now we'll need 2 more statements in the output SPICE net list. Because these won't be related to any components, they need to be put into text blocks to appear in the output. Go to the libraries again with the insert key and select codeshown.sim. Place 2 of these in the test bench schematic. The first one will tell ngSpice where to find the device models for the devices that are used in the schematic. We'll use a .lib statement that selects a top-level file telling ngSpice where to find all the models, but also specifying a simulation corner for the models. We'll use the typical corner, so the statement will be, and remember to put this in quotes, .lib / user share PDK Sky130A libs.tech ngSpice sky130.lib.spice space tt, close quote. For the second text block, edit it with the Q key and change the value, also in quotes, to open quote .control return tran 1in 1u return plot vn vout return .nc and close quote, which will run a transient simulation for 1 microsecond and plot the values for signals in and out. You can put the new lines between the control block statements as long as the whole thing is surrounded by quotes. Then do a save as and save the file, renaming it to inverter_tb for test bench. To simulate, all you need to do is to click on netlist to get the netlist and then simulate to run the simulation. The simulation will take a while to start up. because ngSpice wants to read in all of the SkyWater models, not just the ones we are simulating. I will give this some time to run. Once it's done, it will display a plot of input versus output. Let's give it a few moments to start up. And there it's moving ahead. And now it's done. And here's the plot. The lines should cross at about 0.8 volts. We wanted to display a plot, so we did not add the statement quit to the ngSpice control block in the schematic, so you'll have to exit the plot in ngSpice in turn. Don't exit Xscheme just yet. Now that the circuit has been functionally validated through simulation, we're ready to create a layout. We'll need a netlist that is not the complete test bench, but just the circuit itself. To do this, go back to editing the inverter schematic, which you can do through the menu, or you can just click on the inverter symbol and select it, then type E to edit the schematic. There is one detail that needs to be taken care of, which is to go to the simulation menu and click on LVS netlist. Top level is a subcircuit. This will ensure that we have properly defined the subcircuit for creating a layout cell with pins in the layout. Check to make sure it's done. Yes, it is checked. So now that that's done, click on netlist again. That should be all, so just exit from Xscheme.
Yo no sabía que era así.
El problema es que como no hay gravedad, cualquier tipo de fuerza, no hay nada que, no hay fricción.
Sí, sí.
Now start up Magic like we did before with cd:/mag and magic-d xr. Importing a schematic is easy, at least the basic part of it, if you have a PDK installed. Go to the File menu and click on Import Spice. Let me get the command window up first. Import Spice. From the pop-up window, move to the Xscheme directory where the netlist was saved. Then select inverter.spice, not the test bench netlist, and click on Open. This is a very small circuit, so it all happens very quickly. Like when you start Magic, you get a very zoomed in view after this is done, so at the end, type the V key to get the full view. It should look like this. If anything goes wrong with this process, like forgetting some of the parameters when you edited the components in Xscheme, just delete the .mag files in the mag directory, return to the Xscheme directory, fix the schematic, and repeat the steps. Now, the schematic import does not know how to do analog place and route. As I mentioned in the lecture, that's very complicated, but what Magic can do simply is to find all the devices in the netlist and create them with the same parameters and drop them in a layout. It's up to you now to put them in the best positions and wire them up. As I said at the beginning of this lab, this is not an exercise in doing the best layout, so we just want to make sure it's wired up correctly, not beautifully. Use the I key to select a device instance. Use the what command if you want details. If you want to see the parameters of a device, select the device with the I key and then type Control P to bring up the parameter window as I showed you before. Start off by taking the PFET device and moving it above the InFET device like this. Use the M key to move. It's a bit different than moving something in Xscheme, although there is a pick tool that works more like that. The easiest way to move an instance in Magic is to select the instance with I, move the pointer to where you want the lower left-hand corner of that instance to go, and then type M. Like so. M. And move it back. You can do the same thing to move pins, but use the S key to select things instead of I, like pins that are not cells. But you can use the M key to move them in the same way. I'm using the scroll wheel on the mouse to pan layout up and down. So I'll pan up with the scroll wheel, pan down, and then pan up, and place the pins with the M key. Now, there are some parameters that will make it much more convenient to wire this thing up. Parameters that I mentioned in the lecture are very specific to the layout. These parameters don't show up in the schematic entry, so you can only adjust them as needed in the layout. On the PFET device, select top guard ring via coverage. Need to scroll up here. Yes, find top guard ring via coverage and type 100. This will put a local interconnect to metal 1 via at the top of the guard ring. For source via coverage, use plus 40, and for drain via coverage, use negative 40. This will split the source drain contacts and move one to the top and the other to the bottom, making it easy to connect them with a horizontal metal 1 wire. Now click on Apply. It's a little hard to see the contacts without zooming in a bit. But that's the effect of what the parameters did. Now do a similar thing for the InFET device. When you select the InFET device, the parameter window will automatically update to the InFET. Set the bottom guard ring via coverage to 100, and as for the PFET, select the source and drain via coverages as plus 40 and negative 40 respectively. Then hit Apply. If it all looks good, then hit Close. To wire, just follow what I'm doing here in the layout. I want to connect the VSS pin to the bottom rail, so I put the cursor box covering the pin in the InFET contact, then hover the pointer over the metal 1 area of the pin and click the middle mouse button to paint that type into the cursor box. I do the same thing for VDD. VDD and ground have to go to the transistor sources, so I'm going to connect them up like this. You can zoom in to get a better view of where those contacts are. Here are the sources. I'm going to connect them up with a horizontal metal 1 wire. And connect that up to VDD. And here, connect the sources with a horizontal metal 1 wire and connect down to ground. The drains will be connected to the output like this. Here I'm using a method for wiring in which I start a wire by making and painting a rectangle. I then type the space bar until the pointer becomes an arrow. Then I left click on the end of the wire, and I can use the mouse to extend the wire with a left click to make a new wire segment and the middle mouse button to end. When I'm done wiring, I'll press the space bar several times until I get back to the box tool with the crosshair cursor.
That's huge. Congratulations. Maybe shake your hand.
I'll wire up the input in the same way. The input goes to all of the poly contacts. If the transistor sources were wired up and down to the power supplies on the right side of the transistors, then the gate connections can be routed out and connected to the left. And I'm going to use the wire tool again to do these connections.
I wish I could see how it was before.
If you did that correctly, then you have an inverter layout. As I said at the beginning, you may have DRC errors and you may have wired it incorrectly, but don't worry about that at this point because that's what the other lectures and labs are for. Here, I just want you to understand the flow from end to end. So to finish up, click on Save and then click on Auto Write in the pop-up window. We could do Save All and Quit, but we're not ready to quit just yet. Since Magic has been counting DRCs as we have been designing, you will see a DRC count at the top. There's a way to run DRC in batch and to run full DRC, but we'll leave that now for the next lecture and lab. For now, let's continue with the flow. In the command window, type these commands for extraction: extract do local and extract all. The first command makes sure that Magic writes all results to the local directory. The second command does the actual extraction. The output is in Magic's own format, but we want a spice netlist. So we'll continue with x to spice LVS, which sets up the netlist generator for hierarchical spice output in gspice format and no parasitic components, which are good for simulation but not for running LVS. Then we can do x to spice, which creates the spice netlist. Now we can quit. If you do an ls in this directory, you'll see the inverter.spice netlist that was just generated. You can remove the .ext files if you want, since they're just intermediate results from the extract command. You'll see additional .mag files for the devices. If there are more than 2 devices, you can clean up the directory with user/user/share/pdk/bin/cleanupunref.py -remove dot, which will remove any parameterized cells that were created and saved but are not used in the design. Now for LVS, do cd:/netgen. And run this command from the Linux command line. netgen-batch LVS /mag/inverter.spice inverter /xscheme/inverter.spice space inverter close quote. Always use the layout netlist first and the schematic netlist second, so that you always know that in the side-by-side results the layout is on the left and the schematic is on the right. Each netlist is represented by a pair of keywords in quotes, where the first is the location of the netlist file and the second is the name of the subcircuit to compare. If your circuit was wired correctly, and I'll stress again that it doesn't need to be for the purposes of this exercise, then the output will look like it does here. I see where it has combined the 3 fingers of each FET, and it tells me that each of the circuits contains, after parallel combination, 1 INFET and 1 PFET, and that the circuits match uniquely. If the layout was wrong, then this would be followed by a list of non-matching nets and devices, which is what we will look at in detail in an upcoming lecture and lab. If the layout is correct, then the last thing you'll want to do is to revalidate the circuit with a netlist derived from layout, including parasitics. Magic is not quite up to doing full RC extraction. It can do it, but there are issues with the method that require manual intervention, and which I plan to fix in the near future, so I will stick with capacitance extraction only for this exercise. For that, go back to the mag directory, so cd//mag, and start magic, magic-dxr inverter. The circuit was already extracted for LVS, but if you recall, we used the command x to spice LVS, which sets up the netlist output for LVS, part of which means that it does not extract parasitics. So this time, do extract do local, extract all, x to spice LVS, and then follow that with x to spice C-thresh 0, x to spice, and then we can quit. The x to spice C-thresh 0 tells Magic to add all the parasitic capacitances to the output netlist. If you look at the output inverter.spice in an editor, you'll see that there are a bunch of lines beginning with C. These are the parasitic capacitances. While you're looking at that file, make note of the order of pins on the inverter subcircuit, which is at the bottom. I'm going to cut and paste that part. I'll make a quick test bench out of this by copying the test bench file from Xscheme. So copy /xscheme/inverter/tb.spice to dot. Now the schematic and layout are supposed to agree on the order of ports, but they don't necessarily have to. So compare the call to the inverter against the order of ports that you noted in the layout extracted netlist. So I'm going to edit the inverter tb.spice file, find out where it is calling the inverter, look at what I put in cut and paste, and the order of ports is slightly different, so I'm going to change that to match. Then we'll remove the subcircuit definition from the file, and we'll replace that with an include statement, which is to include inverter.spice, and that will read the layout extracted netlist. Everything else in the test bench remains the same. You can save that. One more thing you need to do is to create the .spice_init file in the mag directory like you did in the Xscheme directory, or just copy the .spice_init file over. So copy from ./xscheme.spice_init to dot. And now run the simulation from the command line. So ngspice inverter_tb.spice. This should run just like it did from Xscheme when we simulated the schematic captured netlist. Once it finishes, you should have a similar plot. And likewise, it takes a while to start up, so we'll give it a chance to run. The parasitics are negligible for this circuit and won't make much of a difference to the output plot. And there it's going, and should be done. And now you can see the plot, and yes, it's approximately the same. So as of now, you have worked through a complete design flow end to end. So now you know how it's done, and congratulations on getting this far.